So you remember how the CD was made from last class, Tuesday? What kind of technique do we use? We had these three kind of molding techniques, and it was one of the three. You remember which one? Injection molding, right? And it's a polycarbonate disc. Now you will see very quickly, if we want to apply a CD for medical diagnostics, where we will have chambers and complex shapes, you know, we might have some liquids in there, you know, we will not be able to use the same exact manufacturing technique as is used for your CDs that play music. And so I'm going to guide you through there, and perhaps halfway through the class you will start recognizing some possibilities on how you would make these compact discs for this specific application. Field is also in the general area of microfluidics. So I'm going to have to tell you first what microfluidics is, and then why we ended up using a compact disc for microfluidics. By the way, next week, Saturday, that's the 31st, I'm giving a TED talk. Some of you know what a TED talk is, right? I will give a TED talk here at UC Irvine. I don't know exactly the time yet. It will be a very simplified version, actually, of this class here today. Okay? So I'm going to explain you first a little bit about why microfluidics, and then comparing all the different ways you could do microfluidics. You know, basically you're dealing with teeny amounts, picoliters, microliters of liquid you want to bring from point A to B. And you have many, many options, perhaps 5, 6, 7 more options actually to propel fluids. And we happen to have chosen spinning a disc to propel fluids. And I'm going to try to justify to you why we thought that was a good idea. So first, why microfluidics? Then comparing the different options you have to propel fluids. And then the topic at hand, compact disc microfluidics, diagnostics on a CD. I will start with giving you some examples on how we use this CD. And you might know by now there's at least 6 companies that have commercialized products based on this principle. So some of my students definitely were part of that, and my group was part of several of these developments. And other people in my group currently might well find jobs in that general industry using compact discs for medical diagnostics. So I will tell you what it is with examples, and telling you about 3 technical issues that we are still struggling with. That is the use of passive versus active valves on a CD. How to bring liquids back to the center. You can kind of imagine if you spin a disc, liquid will go to the outside, right? So we need to come up with tricks to bring it back to the middle. And there's quite a few ways actually on how to do that. And then the detection schemes. You know, we could use, of course, the laser and the optics you have on your CD, but that's only one color, right? And so often you need more colors to do medical diagnostics on a CD. We'll talk about that. And then I'll show you actually some of the commercial CD-based products that are out there. And in the conclusions, we will tell a little bit about the roadblocks for yet more of these products coming on the market. Currently, I have one student who has his PhD, got it a couple of months ago, and he's trying to set up a company, yet another company on CD diagnostics. And so I'm hearing from him a lot of the roadblocks actually he's encountering. So I will tell you a little bit about that. These roadblocks have a lot to do with that cartoon there, something I showed you earlier this year, right? This cartoon kind of sketches this, you know, pessimistic view about manufacturing in the US, that we have lost a lot of it, and there's a big effort underway to try to bring that back. You might have heard about the Obama initiatives bringing manufacturing back to the United States. And actually what we are witnessing is that a lot of the things we want to do, we cannot do in this country anymore. And so that is actually one of the roadblocks. And if you could bring that back, we might be able to faster bring new products on the market. Okay, so let's start with microfluidics. Why? Well, it starts with that cartoon on the top there. What we want to replace is these big centralized laboratories in hospitals where, you know, PhDs, educated staff, expensive staff, has a whole bunch of equipment and does the analysis of whole bunches of samples that come in every day. You know, you see all of, oh, you can't see it here, but they typically are cuvettes, 10 milliliters of blood, right? And then they do analysis for proteins, DNA, blood gases, blood electrolytes, etc. And then these results are sent back to the patient. What we want to do is replace that whole laboratory by a simple CD and a CD reader. And mind you, you know, the CD technology, when was that invented, do you know? When did the Discman come about? Does anyone know that?
15 years ago?
Sir?
10 years ago?
It was 84, pretty amazing, huh? So remember the Discman? So in a way, that whole technology, all that money was pumped in there, and it's getting lost, right? Because very soon no one will use any CDs anymore. And so we are trying to reconvert that whole industry in a way using a Discman to do medical diagnostics. And I will try to tell you why I think this actually has a lot of future, because there's so much sophisticated technology in that simple Discman that actually really fits the medical diagnostic market very well. So what we try to replace through microfluidics is the following, you know. Even in high infrastructure settings, clinical diagnostics today is inefficient and costly. So even in the best laboratories, you need highly trained technicians, several pieces of expensive equipment. You know, say you're after some strand of DNA in your blood because you're suspecting that, for example, you have food poisoning, which would be caused by listeria. Now, listeria would have a specific DNA sequence, and you would want to know, does your blood have that DNA sequence? You will see there's a whole bunch of steps you need to do before you figure out, yes, this person has food poisoning caused by listeria. That today happens in at least 4 or 5 different expensive pieces of equipment. We want to bunch this all together on this simple compact disc, and we're actually pretty close to that. I think to do a DNA analysis, for example, might still take 3 to 4 years, because our solutions today, they're still a little bit too clunky, they're too complex. And so it might be one of you, or several of you, that come up with good answers to the problems, manufacturing problems I will tell you about today. Did you have a question? So several pieces of expensive equipment, large amount of hazardous waste, reagents, biosamples, disposables. That's why you want to do microfluidics, right? You use very, very small, teeny amounts on these CD platforms. You know, instead of using cuvettes, we use small cavities that we have carved out into the plastic of the CD. You also have long turnaround times, 1 to 2 weeks, high cost, and so we want to prevent all of that. We want to make it an inexpensive platform that can be used in a jungle, in a small village, where you might not necessarily have a sophisticated MD analyzing the results. The results would be sent via the internet through a central location where someone can interpret the results, right? And so we will specifically look at maybe the most challenging diagnostic, that is to do a DNA analysis on one of these discs on a CD. So a bit more about why microfluidics, and now specifically for molecular diagnostics. So nucleic acid-based diagnostics holds much potential, especially for the more rapid and accurate diagnosis of infectious diseases. It's probably one of the biggest growth areas within the medical diagnostics. But today, it's slow and very expensive. And so we want to shorten the time and make it much simpler. In a way, what we want to do is the same thing that Abbott has done for blood gas and blood electrolyte analysis. Some of you might have seen this. This reader that is held up here. reads up to 8 or 9 analytes in your blood. You know, it can measure the pH, sodium, potassium, chloride, ammonia, oxygen, CO2, and a variety of other things, depending on the chip that you see there on the right that you buy. And these chips are then put into that reader and then thrown away. And so what you do is you put 1 drop of blood on that chip, insert it, and you get your answer. Now, this is for simple analytes like pH, sodium, potassium. What we want to do is have the same kind of handheld simplicity, but do it for medical diagnostics for DNA, right? And so what you need to do for that is integrate in that handheld all the following components. So let's say you start with your raw sample, blood, right? In this case, we want to separate cells out of this blood, and let's say we're going after bacterium. Now that bacterium has DNA inside, so it means we need to break it up. We need to lyse it. So we need to lyse the cell. Now, when I do lysis, what do I have? I have organelles, cell walls, proteins, DNA. I have a big mixture, right? So I need to do lysis and purification. And then in the case I'm after DNA, I need to amplify it because in many instances I will not have enough DNA there. So I need to amplify it, and then I finally do the detection. So today this happens all in separate instruments: cell separation, cell lysis, amplification, which is PCR, and detection. And these machines can cost, some of them can cost up to $150,000. And so the challenge is to shrink this all down and put it on a CD, on a compact disc, right? And so I will show you how we today already achieved some of these functions you see in that rectangular box at the bottom there. And we believe that if we succeed in that, we will have done the same as Abbott has done with their so-called iStat machine. In other words, they have made a point-of-care machine possible. You don't need to go to that central lab anymore. The medical doctor can, or the nurse can be next to the patient and get the answer 4 or 5 minutes later, right? Instead of waiting for a couple of days. So what does microfluidics do in that process, in that miniaturization and integration of all of these process steps? Well, it helps in the sample preparation, we will see. In the process integration and multiplexing. Multiplexing means very often you don't want to do this just once. You might want to do it 10 times around the perimeter of the CD. So multiplexing just means that these steps you want to do in parallel quite a few times. If you have a small amount of liquid, you might be able to do that. Right? So with that as a background, none of this requires the CD, right? This just requires microfluidics. So the next slide is a comparison of all of the fluidic propulsion methods out there. Before I project that slide, what kind of techniques do you know to pump fluid from point A to B? Could you write a couple of down? I'll just give you a minute, see how many you come up with. This is good because I don't think you have this class on the web yet, so. One that we all know is a pump, right? So a pump will do. Okay, I gave you a good hint. What else can we do?
Height difference.
Sorry?
Height difference.
What?
Create a height difference.
A height difference, yeah. That's a good one.
Electrical field.
Electrical field, electroosmotic, we have 3, yeah. What else? Well, you know one, the CD, right? So it's 4th one. What else?
Osmosis.
Sorry?
Osmosis.
Yeah, electroosmosis. I thought that was the one when you were talking about electrical field. That's the one you were thinking about. Sorry?
Capillary reaction.
Capillary action, sure, yeah. Can also do something like electrolysis of water, so you create a gas that pushes the liquid. So there's so many acoustic. There's acoustic pumps. There's piezoelectric pumps, and on and on and on. So it's almost a zoo out there. And why from that zoo have we selected the compact discs? And the following table gives you some guidance in that. Actually, I skipped one slide. Let me, before I go to that table comparing fluidic propulsion methods, let me explain a little bit this slide. This is a very important slide. My colleague and collaborator for 10 years, Professor Michel Bergeron, who's a medical doctor in Laval, gave us this slide. And he said, this explains why medical doctors want to do medical diagnostics on a CD through DNA. Look, if you go as a patient to a doctor, you know, let's say they do radiology, you can get the results back after an hour. Biochemistry, that's that sodium, potassium, that Abbott instrument, right? Blood gas, blood electrolytes. You can actually have these results back in an hour. That is even if you go to the centralized lab. So that's pretty amazing, but it's because it's so simple, right? So hematology, same. Now where it is very different, that is if you have a bacterial culture and you need to do a traditional culture. You might have to wait a couple of days or even a week. Why is that? Well, in this case, instead of taking the DNA and amplifying the DNA, here you're multiplying your cells. Now, multiplying cells by culturing is much slower than amplifying the DNA that you took out of it. So in other words, what you do in molecular diagnostics, you're doing microbiology without culture. So it's changing to a culture without culture. You follow that? So in microbiology, you would have a cell, culture it till you have many of them. In the case of molecular diagnostics, you don't do that. You take the DNA out and amplify the DNA. That you can do fast. And so that's why this now is kind of old hat, and we can get all of the results within 1 hour or less. That is, when you have to tell the story to a medical doctor, that is what they will relate to. So no more culturing in Petri dishes. So now we come to that table with these different methods for propulsion of liquids. It's not all that clear, so I will read through each of them. So we are comparing centrifugal, pressure, acoustic and electrokinetic. So let me tell you first, make sure that you understand each of them. Centrifuge will be our compact disc. So we're going to pump liquid by putting something in the middle of the CD, and by spinning, you pump it outwards, right? Pressure is your regular pump. Next, acoustic, that is basically by sending acoustic waves over a thin plate and have these acoustic waves unidirectional so that the liquid follows the acoustic waves. It's a technique pioneered by a friend of mine, Professor Dick White at UC Berkeley. And then the last column, electrokinetic, that's the one you were referring to. That's electroosmosis, where basically you apply a charge, a voltage, a DC bias across a capillary, and you will have osmotic pumping enabled that way. So these are the techniques that I'm comparing. There's quite a few more. If you look here, there's up to 9 methods that are described that one could use. But so I've taken from these 9 the 4 better ones, more promising candidates, and we're going to narrow it further down on the criteria in the first column here. So the comparison, first of all, valving. Now this is so important. You can have a valve that works for a liquid, but does not work for vapor. I need to make sure you're all on board with this. Look, if I have that compact disc, right? I wonder if there's a pen here. Let me make a drawing. So on the compact disc, this is the center of the disc. And over here I have a reservoir 1A, and it's connected with a capillary to a reservoir B. So if I have this filled with a liquid, and I start spinning, you all know what will happen, right? So it will go towards this chamber. But say I'm not ready to bring this liquid from here to here. In other words, I have that CD sitting there with some liquids, maybe for 6 months, right? What will happen with this liquid? Will this be a barrier? It will not, because vapor will distribute all over. And so after less than 6 months, maybe even after a couple of days, you know that liquid, because of the vapor pressure, will be everywhere. Interesting, right? Because that means that this capillary here can be a barrier for liquid, but not for vapor. Do you follow that? Right? Because, look, before the vapor spreads out here, the liquid is stuck here because of capillary tension. And I need to put quite some centripetal force to unlock this liquid to make it go to this chamber. I will come back to that later. I will actually show an expression, an equation that shows that at what rotation speed will the liquid actually start moving. We call that a passive valve, but it's only a valve for liquids, not for vapor. And you cannot believe what big problem that is actually for all microfluidics. You know, electrokinetic is the same. You know, you can with that electrical field make the fluid go, but you cannot have that fluid sit there for 2 or 3 months because the vapor will connect everything. So make a big distinction between a vapor valve and a liquid valve. And in manufacturing, in a platform like this that's flat, it's not so easy, not so straightforward to implement valves. So that's what I have there. Is the valving method solved? It says yes for liquids, no for vapor. You understand that point now, right? So indeed, on a CD, I have a valving method for liquids, but I don't have a good valving method yet for vapor. By the way, since it will come up later anyways, what do you think you could do for vapor valve on the CD? The 2 or 3 people that have worked in my group on CDs should refrain from answering, right? So as engineers, think about what could you do to make it such that not only liquid is valved, but also vapor cannot go from here to here. What could you do? Be creative here. You're the engineers, right? Yes?
Can you pressurize it with like something like an inert gas?
That still would have the same problem, right? Because the diffusion of the vapor, the water vapor, would still go against that pressure gradient. That wouldn't help, no. There's actually some simple techniques you might come up with. Yes?
Use some sort of hydrophobic material?
No. Also, that would not work, right? Because the vapor can still go over that hydrophobic material. Be creative. What else could you do? Alex, you're allowed to say it if you know it.
Can you use a barrier of some sort, like wax?
Yeah, wax. Wax is probably the simplest solution you could come up with. You melt some wax here, right? And then this is a vapor barrier. And then before you start spinning the CD, you melt that little blob of wax. And that's actually a solution that Samsung has developed in its commercial product. They actually mixed in that wax some iron nanoparticles so that the laser could melt that wax bubble faster. So at Samsung, they have now developed sophisticated machinery to put these wax valves where they want. So you can see how a new biomedical application has all of these new manufacturing requirements, like in this case, this machine that gives these droplets of wax. So let's go on. Pressure. Yes for liquids and vapor. So this is kind of where we are jealous from our big counterparts, because if you have a pump, you know, you work with bigger tubing, and it's easy enough to have an open and closed valve, right? But us in these small platforms, how can we incorporate one of these big sophisticated valves? Number one, it will be too expensive. Number two, geometrically, it's very difficult, isn't it? So, by the way, you will see that is why pumps, regular pumps, are still the most used propulsion method for liquids today. So next what we have is acoustic. This is actually a little bit worse than the previous one, than the centrifuge one. In this case, there's no solution yet for liquid or vapor. So it's kind of even more of a challenge there. Because this is a complete open platform. You have a surface, and underneath you have that acoustic wave. All it does is bring liquid from point A to B. That's it. But there's no valving method there at all yet for liquid or vapor. And that's one of the reasons, not only that, it's also very difficult to make these acoustic transducers underneath a thin membrane. They use zinc oxide, which is very difficult to pull into good piezoelectric. So engineering-wise, acoustics is still quite a bit behind. And then the last one, electrokinetic, yes for liquids, no for vapor. So the last one is about the same as centrifuge. They have the same problem. Electrokinetic for easily 8 to 10 years in the United States was funded by NASA, DARPA, everyone. NIH was pumping money, money into electrokinetic or osmotic pumping. After all of this effort, no one came up with this simple valve that we need. And we need that valve for centrifuge, for acoustic and electrokinetic. So if you solve it, you do not only solve it for my CD, you solve it for these other techniques as well. So it's a very worthwhile project to get engaged in. And mind you, you can say, well, you could use wax everywhere. It's not a very ideal solution at all. You know, you have to make sure that that wax completely fills the hole, the channel, right? Because if it doesn't, liquid will still leak. Vapor will definitely still leak, right? So, and how do you make sure that that wax droplet always fills exactly the same perimeter? So the efficiency, the yield, I should say, of these wax droplet machines is still very weak, very poor. So there is opportunities here for you young guys to come up with inventions, with new technology. Maturity of the technology on the centrifuge, you will see in a moment, products are available. So it doesn't mean that you know, the lack of these valves has stopped products from being introduced. You will see there's easily 6 companies now selling product. So in case of pressure, of course, many products, I would say 95% of medical diagnostics still uses pumps. Acoustic is in the research phase. Electrokinetic products are available, but most have been taken off the market, and most companies that were in that arena have gone broke. So the landscape is full of victims. A power source, so the propulsion force is influenced by, that's important. So, you know, that liquid that you're using could be very different from sample to sample. Could be milk, could be blood. And you don't really want the pumping force to be dependent on the nature of the liquid. And so with that in mind, if you go across in the row, propulsion force influenced by, in the case of centrifuge, it's the density and viscosity that dictates the propulsion. You'll see the equation in a little while. But not pH, you know, not ionic strength, things that will influence the electrokinetic method. In electrokinetic method, pH and ionic strength is different, the pumping strength is different. That's not very convenient, is it? Because almost any liquid that you use will have a different pH, will have a different ionic strength, and the pumping force will be different. In other words, electrokinetic pumping depends on the sample nature. It also does a little bit in centrifuge, but density and viscosity usually do not change that much. Right? Definitely not density. Viscosity, by the way, is an issue, because actually depending on your disease state, the viscosity of your blood might be different. And that's a challenge that one has to overcome if you do blood samples on the CD. But it can be taken care of. You know, we have mechanisms, for example, where we diluted the blood so that we always have the same viscosity. In the case of pressure, it's generic. In the case of acoustic, generic, it means these pumping forces are not influenced at all by the nature of what you pump. So for that characteristic, these two pumping methods are better. Power source, in the case of the CD, it's your Discman. It's a very simple rotary motor, very inexpensive. In the case of pressure, you know, it's a pump or a mechanical roller. Acoustic, it's basically a voltage from 5 to 40 volts. In the case of electrokinetics, it's 10 kilovolts, making it a little bit dangerous. You don't want to give everyone a 10,000 volt power source to play with, or you might have some incidents, some accidents. Fortunately, though, it's mostly very low current, big voltage. So your hair might stand up. That's about it, okay. The materials used, plastics in the case of CD, plastics also for most pumps and conduits that you use for the fluids. In the case of acoustics, piezoelectric, quartz, zinc oxide, for example. And in the case of electrokinetic, either glass or plastics. The next line is a very important one for you to know and understand. It talks about how does that pumping force scale in each case. And so I want you to understand that very well. This might well be something that I'm quizzing you about in the finals. What I'm saying there is this. Look, if I'm going to start with pressure pumping. You probably all have that same intuition. If I have a pump here, and the capillary or plastic tubing that I use becomes thinner and thinner, what will happen with the pressure? So if my tubing is thinner and thinner, what will happen with the pressure?
The diameter gets smaller?
Yeah. So the diameter gets smaller and smaller of the tubing, the pressure shoots up dramatically, right? There's actually something I'd like you to check again, Poiseuille's law, that gives the relation between the radius and the pressure. And it goes as 1 over r to the 4th. So that pressure, as r becomes smaller, shoots up dramatically. So what that means is it's very difficult to miniaturize that technology, right? Because if I would want to pump liquid to, let's say, 100 micrometer capillary, I will have to really have a lot of pressure applied. So that is a big, big negative on using pumps in biomedical equipment, especially if you want to miniaturize that biomedical equipment. So you can kind of put a big cross there, and what I've wrote, it scales as L to the 3rd because it's a volume scaling. It scales with the volume of the liquid you're pushing. Now, if you go to electrokinetic, and that is actually why electroosmosis and electrokinetic pumping was so popular for a long time. In that case, the pumping happens because of the charge on the walls of the capillary. Now you can imagine if that capillary becomes narrower and narrower, the fluid in that capillary feels that force better and better. In other words, there the scaling is just the opposite as in the case of pumping. Because the smaller the capillary, the better you can pump. So in terms of scaling, electrokinetic is a really, really good one. Unfortunately, the pumping force, excuse me, also depends on the pH and ionic strength of the medium. So that scales as L square. Acoustic is also a surface force, scales as L square. So if you have a smaller channel, the acoustic energy can better couple with the liquid, and it becomes a better pump. In the CD, unfortunately, that scales more like L to the 3rd. So electrokinetic is better for very, very small samples that are very pure. A CD is better for bigger samples, but they don't need to be so pure. And so that was kind of the decision you had to make. If I use electrokinetics, I need to purify the hell out of the sample before I can pump it. If I use a CD, unfortunately the scaling isn't all that great, but I can deal with milk, urine, any sample, you can pump it easily. You could not do that with electrokinetics. Good? Flow rate, so scaling, then flow rate from less than 1 nanoliter per second to greater than 100 microliters per second, so wide range with the CD. With pumps, even a bigger range, we all know that, right? You can literally pump buckets. Acoustic published results show something like 20 microliters per second. And then electrokinetic can also go very, very small because we know that scales better in the microdomain. You can literally do picoliters there per second. So general remarks, kind of concluding over all of that. Centrifuge, you're working with an inexpensive CD drive. Mixing is easy. Most samples are possible, including cells. You would have a hard time doing cell work with electrokinetics. The cells would go against the surface, change the charge, and basically your pump is dead. You know, so, but you can work with cells on a CD. Pressure is a standard technique, but it's difficult to miniaturize. Poiseuille's law, right? You make the radius of the conduit smaller, pressure goes up dramatically. Then acoustic is still very researchy, least mature of the techniques. And then electrokinetic, high voltage source is difficult to handle. It's very good for small samples that need to be very pure. There is one aspect that I have not explained well yet in this, that is the mixing. Look, it says here mixing is difficult, and here it says mixing is easy. I need to explain that a bit. Look, if I have an electrical field to drive a liquid, how can I do mixing? Because to do mixing, I need to create a space, a volume, where the other liquid can come in. That means there might be an air bubble or something, and your voltage will go to pots, right? So you would have an overload. In the case of my CD, it's very easy. I bring in one liquid from one chamber, another liquid from another chamber, join them in one common chamber, that there's air in there, who cares, right? So mixing is easy in that case. It's very difficult in the case of electrokinetic. So that table, please study it a bit, because there will be a question coming out of that. And it kind of sets the stage for why we have chosen this. Over all of these techniques, we have chosen a CD, centrifuge, as the ideal method for pumping liquids. But it's not only that. You will see in a moment there's many other reasons that kind of conspired to make that an ideal methodology. So, and these additional reasons are mentioned here. So why a CD as a diagnostic platform? So before giving you more reasons, I need to tell you, or remind you at least, how a compact disc player works, right? So you remember from last class already how we make a CD, right? We have this polycarbonate, we have an aluminum layer, and you have these tracks. You can see the CD running there, and there's lands, right, and islands that are coated with an aluminum layer. There's a laser shooting. So I'm looking at the label of the CD, right, and then the label is on top. So the laser shoots from the bottom through the polycarbonate, and it hits that aluminized layer. And when the light sees an island or a land, different amount of lights will be picked up by the photodiode. And that's translated in a 0 to 1, so you get a signal passing by over there, a digital signal. You can, of course, convert that into an analog signal, and then you have sound, music, whatever, right? So what we are kind of saying, it's not only the fluidics of the CD, we use the whole infrastructure of this optics, in other words, of the discman of the player as well. Why? Well, it's a tremendous benefit of piggybacking on a technology that has been developed with billions of dollars, you know, to make a platform very inexpensive. If you would have to develop this afresh, there's no way you would have enough traction ever to develop for medical diagnostics. But it was developed for the entertainment industry, right? And so there's a lot of money there that created this fantastic little machine. So what does it really do? The fundamental job of a CD player is to focus the laser on a track of bumps. You see that there on the left. The laser beam passes through the polycarbonate CD material and reflects off an aluminum layer and hits an optoelectronic device that detects changes in light. So the optoelectronic device is that photodiode there, right? The bumps reflect light differently than the lens, which is the rest of the aluminum layer, and the optoelectronic sensor detects that change in reflectivity. And by the way, this is already another kind of very nice application of the CD player. If you want to find a song on the CD, you can do that, right? You can actually go to that place where that song is recorded. That means your CD player is an XY stage. In other words, you can find any spot on that CD. So what I will do, if I put the DNA array there, I will know where each spot of the DNA array is located. That is very powerful. I don't need to develop that anymore, it's there. So a tracking mechanism moves the laser assembly so that the laser beam can follow the spiral track. The tracking system has to be able to move the laser at microns resolution. So there is two motors. I'm sure some of you have opened a CD player. There is a rotary one, and then there's a tracking motor, a linear one. And that mechanism allows you to go anywhere on that XY platform. So now I will surprise you. I will show you how you can exploit some of this in a complete different way. In three different ways. First of all, you might not have considered that, but what I just described you here in that line, look, go back here. What do I say? The fundamental job of the CD player is to focus the laser on a track of bumps. Now, if I put, instead of little pits there, I take the wing of a fly and I put it on my CD, I can actually make the image back of that wing of the butterfly. In other words, it's a microscope. So your CD player is a microscope, and it's a good one. It has a resolution in the micron range. And so here on the top, what you see is an image of a gnat wing made not by that microscope, but by your CD player. Now, what do we use often in medical diagnostics? Microscopes, right? And so, okay, I got that, right? By the way, on top we show an immunoassay where you see the dots of the protein array. Now the next one is kind of easier to understand. Spinning a CD, that's just like a centrifuge. Now what do we also use a lot in medical diagnostics? Centrifugation. So that dumb thing, that disc man, is also a centrifuge. So number two. Number three, well, what do we use a lot in medical diagnostics? You need containers for liquid, right? So you have little cuvettes like this, or you use glass slides, and what we do is we use the plastic of the CD to replace all of those. You can make those CDs for 10 cents. Yes?
So the microscope using the CD is just a black and white, right? Because you can only shine laser.
Right.
0 and 1.
Right. It would be so good to also have a team building a microscope based on that here at UCI. I have currently a team of students in Monterrey Technologico in Mexico building this. Because I told them about it and they got so fascinated they asked if they could do it. Oh, and by the way, one person said, but why would I use this? Why not use a CCD camera and just image on that wing? Can anyone answer that? Do you understand? So that was a very clever question, right? So why go through the effort of spinning this thing and reconstituting, you know, from your photodiode the signal back to the shape of what's on there? Does anyone have an idea why that would be? It's because I can image over the whole CD platform, right? So I could have 100, 200 different things. Right? So if I would use a camera and I need the same resolution, I would have to move anyways to these places, right? So if anyone has an interest in that, could connect you with the team in Mexico, And maybe someone, I always had hoped that someone would build a little toy for kids based on that. Right? I mean, you could just have 10 CDs in a package, and the kids could put on a hair, or they could put on anything, right? And then on their screen, they would see the object that they are imaging. And you would have a company. So anyone is interested, I can connect you with the folks there. And so you have an affiliate in Monterrey, Mexico, and we set one up in Irvine. Microscope on the CD. So now that I told you a little bit about why microfluidics, and then I honed into why microfluidics on the CD, and then I said, look, it's not only the CD, right? It's also the reader, the whole infrastructure of a CD player. Now I have to start showing you applications. Applications going back to this diagram here. Remember, we want to do all of this on that CD, right? And to get you to understand how the CD works, does any of those, I'm going to single out this one. I'm going to show you how we do cell lysis on a compact disc, right? And I'm going to go over it slowly, step by step, because if you understand this one, you will really kind of get a hang of how the CD works. So imagine your polycarbonate disc, and the elements I have carved into that polycarbonate disc are shown here. I might have 10, 15 of these elements all around the perimeter. And what do we have in there? So the blue, so just focus on this drawing in the middle here. And these are chambers in the CD. So the blue is an open hole. So that blue hole, the biggest one there, is close to the center of the CD, and that's where I will bring in my sample. Let's say I have that teeny blood sample, I will introduce it in that blue hole. Then the yellow first chamber you see is 1.4 millimeters deep. And of course there's a cover, right? So you have basically two polycarbonate discs, imagine it that way, and there's a chamber in there. And that chamber is connected to a second chamber, same size, and also 1.4 millimeter deep, but the red area, notice, is only 0.1 millimeter deep. It's very important to notice that. Good? And then you can see I have a red siphon connecting the second chamber to a collection round chamber. That's again 1.4 millimeter deep in yellow. You can also see that that top chamber has a disc, right? That is a metal disc. So are you all with me so far? So we have these two chambers connected with kind of a capillary, right? And then we have a siphon, and that top chamber has a metal disc. Now under the plastic, under that polycarbonate, I have permanent magnets. You can see them here. Right? I will also, this is a movie we will look at a moment, but so you see all of the same elements, right? That's the top chamber, that's that chamber, and then I have a collection chamber corresponding with this. And then that black thing you see there, and there, and there, these are these magnets. So now, you imagine I have these magnets fixed here, and that disc will move over these magnets. The magnets don't move. Now, when the disc is rotating, you can see that that metal disc has different distances with respect to these permanent magnets. What that means is this disc will be attracted to these magnets underneath, right? So as I'm passing by, what it will cause that magnet to do like this, up and down. So as the disc goes around, in that top chamber, that disc there goes up and down, because as it moves, it gets attracted to that top magnet, then to this one, and so forth, right? So the metal disc moves up and down because it follows the magnet underneath. Now, what I will do is cause a crushing motion. Because what I want to do is lyse cells. Now, how do I lyse cells? Well, in that chamber, I put the cells, I put glass beads, plus that metal disc. That metal disc moves the glass beads that are ripping along the cell walls and rip it apart. And in no time, that top chamber will be filled with cell debris, DNA, proteins, etc. It's like a mixer, right? Vortex. And at that moment, I have done the first step. I have lysed, broken up the cells. So what I have done, step 1, lysis. At 100 RPM, I have moved rather slow. Why? Well, that metal disc, if I go much faster, will not follow, right? 100 RPM, it can't follow. So now, next step. I suddenly, when I'm finished with breaking up the cells, I change the RPM from 100 to 6,000. Why do I do that? Well, you can see that red area there, that forms a constriction. It's very hard for liquid to go through there because of surface tension. In other words, it's a capillary valve. And I need to move the liquid in that top chamber with enough force through centripetal action, centrifugal action, to overcome that surface tension. So at 6,000 RPM, that valve here, you will see in the movie, will burst. And liquid from this chamber will be transferred to this chamber. What will not transfer is that big metal disc, because it cannot go through this. The glass beads will not transfer, but all of your mixing cocktail will transfer to the chamber at the bottom. Are you still with me at this point? Yeah? Okay. So now the next thing is purification. Purification and centrifugation. So imagine that liquid from here has come to this chamber. And now I'm going to do centrifugation. What happens in centrifugation? You remember what happens in a centrifuge? So what will accumulate here at the bottom? The big junk, right? And then if I go up, it will be purer and purer, right? So the DNA and proteins will be higher up. Organelles and so will be at the bottom. Now what I want to do, I want to siphon off the top fraction, because I don't want to have the junk. So that siphon here, you can see where I've put it. It comes here, right? That means if I would succeed in transferring liquid above that T-junction, only nice, clean DNA and protein mostly would transfer, and the big junk would be left behind. But how do I do that? Look, while I'm spinning, there's no tendency whatsoever for the liquid to go up into that capillary, although that capillary, and I neglected to say that, is hydrophilic. Polycarbonate is hydrophobic, so that whole disc overall is hydrophobic. But that capillary, I've made it hydrophilic. So the liquid would want to go there if it only could. How can I make it go up there? By reducing the RPM. Because if I go back to lower spinning rates, the centripetal force pushing on the liquid is less, and now it can go up there. So let's go over each of the steps again, and I want to make sure that I have everyone with me and understand it before we look at the movie. So we start with spinning that disc at 100 RPM, rather low, and that allows that metal disc to do like this, chuk, chuk, chuk. And you'll see that in a movie, and it basically crunches up the cells. It makes a cocktail. Then I transfer to the clarification chamber, meaning the second chamber, and I do that by upping the frequency dramatically. I go from 100 to 6,000. Because of that, the surface tension pinning the liquid here is overcome. I will show you an equation that describes that a little bit later. Now liquid from here can transfer in this chamber. Good? I do a little bit of centrifugation to let the heavy particles settle at the bottom, have the DNA and protein fraction layer up on top, and now the top fraction that's above the T-junction here of my siphon I want to transfer. What do I do for that? I go from 6,000 to 100. That's priming the siphon. It means I allow that capillary to do its action because it would like to do it anyways, but it couldn't because the centripetal force was pushing the liquid down. But by reducing the RPM, it can fight against the centripetal force because it's much smaller now, and it can go up into that elbow. Because you realize, I'm going against the centripetal force, am I not? I'm going back to the center, right? Going up in that elbow is going against the centripetal force. That means that my capillary action must be stronger than the centripetal force to do that. And then once the siphon is wetted, it's primed, we can go up a little bit faster and then finish all the liquid into this chamber. So let's watch the movie. Any question before I show the movie on this? Do you all understand the action of this lysing process? Yeah? Okay, so let's look at the movie. So that was fast, right? Lysing was done already. Now it's transferring to this chamber, and you can see it goes above where the elbow enters the chamber. But nothing goes up yet, right? Nothing goes up in the capillary, nothing goes up into that elbow. That will only happen when I slow down. And now I have transferred, and so that liquid collected here now is purified DNA. And what do I do with that? Well, I need to amplify it. I need to go to detection eventually and integrate all of that onto one CD. But at least you understand kind of the overall action of how you employ that CD. What I'm going to introduce, and that's going to be about the last thing I will do, because I think I gave you quite a bit of new stuff, and then on Tuesday I will finish the rest of this class. I want to discuss a little bit, coming back to this issue here, that is active versus passive valves. Look, the CD fluid propulsion is achieved through the centripetal induced pressure and depends on the rotation rate, geometry, and location of channels and reservoirs and fluid properties. We actually have now programs that pretty much, we put the reservoir there, it has this size, capillary width is this size. We can pretty much do any complex chemical handling on a CD. And the simple equation controlling all of this is given here. So imagine, to understand all of the parameters in that equation, we have the center of the CD as indicated, and then I have a liquid plug that you can see with a top reservoir and a bottom reservoir. You see an R bar as defined there. You have an L, a length of the capillary filled with liquid, and you have a delta R. Now, the picture on the right describes how a liquid will get pinned and cannot escape till you go fast enough so that that bubble bursts. We call that the burst frequency. So I want to calculate how fast do I need to spin this CD for the centripetal force to overcome the liquid tension, the energy keeping that bubble together. And that expression is given here. So this term is the centripetal force, right? It has omega squared, that is the rotation speed in RPM, right? R and delta R are defined in there. Rho is the density, right? So density, spin speed, and basically the location of the liquid element in the CD is 1/4. So you calculate that. Then you compare that, you contrast it with the surface energy, the surface tension of that bubble. And what do I have in there? Well, I have gamma, the surface energy. I have the contact angle between the liquid and the solid. And I have a hydraulic diameter. The moment that the centripetal force, PM, is larger than the capillary force, that bubble will burst. That is a passive valve. I don't need to do anything else. All I need to do is change the capillary width, and I have another burst frequency. Let me try to illustrate that. Suppose that that capillary there has different diameter from 100 microns to 500 microns, and I start rotating. Which one will release the liquid first, the 100 microns or the 500 microns? For which one do I have to go to higher frequencies? I want to see if you get a feel for this. I'll do it again, right? So I have capillary 100 microns, 200, 300, 400, 500, and they're all next to each other. And they have the same liquid here on top. And I'm starting to spin. Which of these capillaries will let the liquid go first? 500, very good. Right, because there the liquid is spinned less. If I go to the 100 microns, the liquid is spinned much stronger. I have to go to higher RPM. That means I have a valve that depends only on how fast I spin. And that's kind of neat, right? I can put 8, 9 functions on that CD and design it such that because of the capillary size or depending on where they are on the CD, this one goes first and this one, this one, this one. We have done systems where we had 7 steps. And that is equivalent to you opening 7 valves. But I don't need to do anything, right? All I need to do is program the computer, and the CD spins at different rotation rates. I have these different actions. That is passive. There's no thing opening and closing there. Now, unfortunately, that passive valve suffers from this. You remember the dilemma? This structure here, that structure there, same thing, right? Is a liquid valve, but not a vapor valve. So if I would have that structure on a CD with some liquid, and I look back 2 days later, the liquid is everywhere, right? Because vapor has distributed over the CD. And so we see now companies that are implementing some passive valves where they can, and some active valves, trying to make clever combinations. Our own group, and I will show you that on Tuesday, has started developing alternative valving methods. And maybe by Tuesday you guys come up also with some other ways on how to do it. Don't do it with mercury. So often I hear, put some mercury there, because then you could kind of, right, have that liquid metal removed perhaps, but who wants mercury in a medical device? I don't think you would be very welcome. But come up with some intelligent alternatives for that problem there. And by the way, make it such that the valve doesn't require any energy to stay closed. Give you an example. We have often worked with ice valves. What is that? Well, I put a cooling element underneath this capillary and I make the liquid plug ice. Nothing will go through it, right? But I need to keep this thing cold. And so I keep on spending energy. That's not too cute, is it? So we need to develop a valve that's normally closed but does not need any energy to be closed. If you understand that, you understood that little cartoon there on the right. Okay, so let's stop it here, but I could take some questions. Otherwise, we'll do the rest of this class on Tuesday.